Steep CarbonTrans presents Towards CO2 Neutral Mobility. Why CO2 neutral liquid fuels? To date, the transition in the mobility sector to lower carbon footprint has largely focused on developing alternatives to petroleum-fueled internal combustion engine vehicles. Besides battery electric vehicles, hydrogen fuel cell vehicles are also gaining increasing market interest. While these developments could support the transition in the personal and public transport sectors towards CO2 neutral mobility, other transport sectors, in particular aviation, but also shipping and heavy load vehicle sectors, have no alternatives to liquid fuels in the foreseeable future. Hence, there is an urgent need to develop economically viable solutions for the large-scale production of CO2 neutral liquid fuels for such transportation sectors. How can CO2 neutral liquid fuels be produced? There are two technological routes to produce CO2 neutral liquid fuels. The first route is based on carbon capture and utilization and consists of two key components. First, CO2 is captured from exhaust gases emitted from point sources such as waste incineration, chemical, steel, or cement plants. Second, H2O is separated into H2 and O2 via water electrolysis. Using H2 to chemically react with the captured CO2, we can produce power-to-X fuels, also called PTX fuels. When renewable electricity is used for electrolysis, the hydrogen generated is called green H2. In using green H2 to convert captured CO2 to PTX fuels, CO2 neutral liquid fuels can be achieved. The second route is based on chemical utilization of biogenic waste. Biogenic waste, such as wood and agricultural waste, are renewable carbon resources, which are CO2 neutral. Using such biogenic waste as raw materials, we can produce syngas, a mixture of CO and H2, through waste gasification. This involves breaking down large organic molecules into small CO and H2 molecules under high temperature and pressure conditions. Syngas can then be converted into the chemical compound methyl alcohol, CH3OH, which is a clear, colorless alcohol commonly known as methanol. Methanol can then be synthesized further into complex molecules called olefins. In the next step, olefins can be oligomerized into liquid fuel products such as petrol, diesel, and kerosene. We call liquid fuels produced this way synthetic fuels, in short, synfuels. During the waste gasification process, in addition to syngas, CO2 is produced. Using green hydrogen, we can convert this CO2 to more CO and H2. This means that all biogenic carbon can be converted to syngas, which can then be processed further into liquid fuels. As both biogenic waste and green hydrogen have zero carbon footprint, synfuels produced via the waste to synfuels route, we call these WIN fuels, will be CO2 neutral. PTX fuels or WIN fuels. A key question to consider in producing CO2 neutral liquid fuels is, what are the advantages and disadvantages associated with PTX fuels and WIN fuels? First, let's consider PTX fuels. What makes carbon capture and utilization so attractive to politics and industry is that carbon-intensive industries such as waste incineration, chemical, steel, or cement plants can continue with business as usual. The significant amount of CO2 which they emit in their production process can be captured as point sources. The CO2 can then be used to substitute primary carbon resources for a wide variety of utilization, for example, producing PTX fuels. Imagine we were using CO2 from waste incinerators for PTX fuels. In waste incinerators, waste is combusted to produce electricity and heat. Through the combustion process, carbon contained in the waste is emitted 100% into the atmosphere. This CO2 is essentially a chemically dead gas. Like a patient who's undergone cardiac arrest, where a lot of electricity is required to get the heart pumping again, In the case of PTX fuels, a lot of electricity is needed to generate enough H2 to energize the captured CO2 for PTX fuels. What does a lot of electricity mean? As you recall, PTX fuels will only be CO2 neutral if they are produced with green hydrogen. To generate 1 ton of CO2 neutral PTX fuels per hour, we will need 32 megawatts of renewable electricity for green hydrogen. Consider that the largest water electrolysis plant, which is currently being planned in Hamburg, Germany, has a capacity of 100 megawatts. Hence, 1 ton of CO2 neutral PTX fuels already require 1/3 of green hydrogen, which the world's biggest water electrolysis plant can produce. Next, let's consider wind fuels. What makes the production of wind fuels from biogenic waste an attractive alternative to PTX fuels? In comparison to waste incineration, where 100% of the carbon in the waste is emitted as CO2, only 50% of the contained carbon is emitted as CO2 in the case of waste gasification, meaning 50% of the carbon in the waste is fixed directly into wind fuel molecules. To convert the remaining 50% CO2 into wind fuels, we need only half the amount of green hydrogen that PTX fuels require. This means in order to produce 1 ton of CO2 neutral wind fuels, we require only 16 megawatts of renewable electricity, compared to the 32 megawatts which is needed for the production of CO2 neutral PTX fuels. To summarize, if green hydrogen is not available or economically feasible, PTX fuels cannot be produced as the captured CO2 is missing its partner for the conversion. That is not the case for wind fuels, as H2 is already available from the syngas. For PTX fuels, green hydrogen is a must. For wind fuels, it is just an option to convert the remaining CO2 into even more wind fuels. A short animated film by the junior research group Global Change, Steep CarbonTrans, at the Institute of Energy Process Engineering and Chemical Engineering, TU Bergakademie Freiberg.